So, uh, this week we started talking about processor design. Um, we said we have different steps for designing a processor. We start with instruction set, and then after instruction, when we know which instructions we need, what is the second step? What is the next step after instruction? Do you remember? Finding which components we need for those instructions, and then we need to connect them to make a path. We call it data path. That was one of your questions, I think. The data path it was for load. I don't remember exactly. Yeah, I think it was for load. So you need to specify which data path, which components connected together to do load instruction. Start from program counter to memory, for example, and put the result back to register file. So that's a data path. After data path, we need to kind of refine data path, adding some other stuff like multiplexer, and maybe we need some extra gates. We do those things, and then define control signals and define controller. So today we want to talk about controller mostly, how we can define that. Sometimes you have multiple controllers in your processor, like in this design that we're going to talk today. We have two controllers, one main controller, one just for ILU. You can have multiple controllers. You can define controller using just Verilog, for example. But in that example, because it was very small in your project, probably you don't need to have a separate controller. Controller can also be done inside, processor. Anyway, but today we want to consider controller as a circuit, combinational circuit, is not sequential, that create these control signals. We have lots of control signals. We're going to see them today. So we're going to talk about that today. But from last class, one slide remains. We're going to cover that before going to the controller. And that is a very important part, how we can synchronize logic design using clock, for sure. When your logic, when your circuit is a sequential circuit, you need to have clock. And this clock gonna synchronize everything. So we need to connect clock, same clock, one clock to all memory elements, registers, and memory as well. So all registers need to be shared with the same clock. This is important. They all need to connect with the same clock. Okay. Oh. Another part is that you need to trigger it with the edge, not level anymore, to make it more controllable, more stable. Because when is the level change, level is sometimes big, and in that case, so many things can happen. You need to make it as short as possible. That's why we are edge triggered, rise or fall. Doesn't matter. We mostly work with rising edge. So it means between two edge, you have time to do whatever combinational things that you need. So at the clock edge, registers capture new data. And between edge, as I mentioned, you have time to compute all the results in combinational logic. Because combinational logic sometimes has different levels. Do you remember levels in digital logic? We have different levels in digital logic. So for example, we can have something like this, and it's going to OR, and and maybe we have one not here. So how many level this circuit has? 3, yes. Because if we consider and also one layer, it has 3 layers. So do you remember the Boole law? Boole mentioned that you can actually implement any circuit in just 2 layers. That's a rule. And we can. We always can do that in just 2 layers. But the last OR probably going to be too big. So that's not very efficient to have many inputs for one gate. Anyway, so that's also something that we need to consider. So this is, because these gates have propagation time, those combinational logic going to make a delay. That delay going to consider the longest one, the longest delay consider for computing clock, but we need to consider other factors as well. We're going to see that now. It's not just combination delay, also other factors that we're going to consider, because we need some stable time for getting it stable. We need some time wasting in the flip-flop, and even if we have multiple registers, this clock, it takes a little time to move from one register to the other. So many factors involved to specify clock cycle. So in general, clock cycle has these 4 parts we need to consider. Clock to Q delay, longest combinational delay, setup time, and clock skew. What is those? The definition of them is here. We can explain in this picture. Clock to Q is a time for register output after clock. So imagine in this picture, this is the combinational part. Okay, and this is the clock that connecting to 2 registers. This is clock connecting to 2 registers. They are registers. That's a combination between, and we want to synchronize this circuit. Let's see what is this cycle time. This cycle time needs to be bigger than a summation of all of this. Let's see what is those. I'm guessing that the clock should be something like this. Okay, rise time. This clock time between 2 rise edges need to be bigger than this. Other than that, it's going to be problem. What are those? I'm going to explain. Let us change this color. Okay, the first one, the time between, in this combinational logic called combinational delay, delay. So this is one of them. We need some time that signal passing inside the flip-flop. That time called clock to Q. Q is the output of the flip-flop, remember? Clock to Q delay is that time. Let's change it to another color to illustrate that. That is this time. Clock to Q delay. We have another time that is called setup time. Setup time, I explain here. Data must be stable before clock. This is the stable time, like setting time. We call that setup time. So we have clock to Q time or delay. We have a combinational circuit delay or longest combinational circuit delay, and we have setup time. And we have another time that we call it clock skew. that this clock skew is the time that passing between these two. If you have multiple sequential circuits or registers, for example, in this case, there is a little delay between these clocks. That's actually called a clock skew. That is time for example, you have two A and B. T for clock A minus, or maybe B minus A, because it needs to be positive. B minus T clock A. Clock A. So this delay, we compute this delay and we add that also in this actually constraint. This is a timing constraint. This is very important. In practical, when you are designing a circuit, you need to consider that. Maybe when you use, for example, Carnot map or other methods to design the sequential circuits, you don't consider that in actual theory, but in practice, you need to consider that always. You need to always consider that a little bigger than that, to everything be stable and everything works great. That's very important. That's called synchronization of logical design. And that constraint is very important. Any question about this? Okay, that was remained from last class. We also talked about control signals last class. We said components that we are using, like register file, like ILU, like data memory, like multiplexers, they have some input, they have some output, and they have some control signals. For multiplexer, we call that select. Sometimes it's 1 bit, sometimes it's multiple bit, if you have multiple input. Anyway, in this computer that we are designing, and is part of your project as well, we consider these control signals. Control signals are the output of the controller. So in this class, we're going to learn how to design a controller to get what and make this register write, register, memory read, and rest. What is the input for this circuit? First of all, this circuit is a combinational circuit. It's not sequential. It's kind of decoder. So what is that input? How controller can understand which signals need to be on, which signals need to be off? Instruction. Which part of instruction? Opcode. Opcode instruction, 7 bits in RISC-V, first 7 bit, like least significant bit, is actually opcode. Opcode, 7 bits, gonna go in, and controller gonna decide which output need to be 0, which output need to be 1. Like in some case, for example, ILU operation, this might be more than 1 bit. Okay, we're gonna see that. So this is how controller work. Let's see, for example, for R-type registers and load and store registers, which actually controller inputs we have. The data paths for this type of instructions, I mean R-type, and load and store is like that. However, we have a program counter here that I didn't consider. This is program counter. What is after program counter? instruction memory, instruction memory. After instruction memory, we have one register that called actually instruction register, I register. Okay, that's a part of data path 2. Program counter, instruction memory, instruction register, register file, ILU, data memory. This is data memory, and the result going to come back again in register file. So the data path, the longest data path, start from program counter, this, and come back, write it again. And longest path is for load and store instructions. Okay, so in this example, we want to see what is this control signals for R type and load and store. Let's go for R type. R type. So R type is like add. You are dealing with 2 registers and putting result in another register. So let's see, what about register write? We are writing the register back to R3. So what need to be register write? This one, this one, 1 or 0? 1, because we are writing back. So this is 1. Okay. I want to show you how controller works. You need to have these values to give the controller, and then make a circuit for the controller. You need to have, this is the values that you need to put in a truth table. You have a truth table for controller, and you can design controller using Karnaugh map, whatever, or just Verilog easily. So these values are important. You need to know, for example, for R type, register write need to be 1. What about this ILU source? This ILU source is an input for the multiplexer that telling you the input of this ILU coming from register or immediate. For add is coming from register file. So this need to be 0. I just put 0 here. Okay, so this blue one is a value for R type. Okay, let's go for ILU. What is this ILU operation? Because we are doing add, is add. Whatever we consider for add, like for example 0, 0. If the number of instruction is just 4, just need to have 2 bits, for example. If it's more, you need to have multiple bits. So whatever we consider for add, going there. Who make that bits? The controller make this based on the number of instructions. Okay, let's go for memory. We have memory write and memory read. What is memory write for add? Do we use memory? No, so it's 0. For memory write is also 0, because we don't need writing or reading. And what about memory to register? What we need to put here? So memory to register showing the write back gonna be from ILU or from memory? It's from ILU, isn't it? So this is gonna come here. So this multiplexer need to have 0 here to let we have this bridge. We have a bridge here to not use data memory. So this needs to be 0. So 0, 0, 0, add 0, just 1. So the output for R type is like that. Register write 1, ILU source 0, ILU op add, memory write 0, memory Oh, memory read 0 and memory reg 02. So all 0, just 1. This is 1. Add is also 2 zeros in my design. But anyway, this is how we design. So we find for our type, this is input, and then go for others. For each instruction, we can write them up, and then this is an input for that truth table. We make a truth table. And these signals are output that we need to find them. Okay, we're going to see that how to design. Any question about this part? For load instruction, we have different values. Any question about this? We're going to do for load. Okay, let's see what is for load. Let me clean this up. For load, we're going to use another color. Okay. Okay, what about when we do load, we are actually adding one register with the immediate value and then read the memory and put the result in a register destination that here is R5. Okay, so register write still is 1 because we need to put the return back here. What about this source? Are we going to get this from immediate or from register 5? From immediate. So this needs to be 1. Okay, the green is for load. What about ILU? Still we do add. Why we do add? Because we need to add this actually index with this space to find the new address of the memory. Okay, what about memory? Are we doing reading or writing? We are loading, so we are reading. Okay, so when we are reading, this is 1, and memory write is 0. And the data coming from data memory this time, so as you can see here is 1. So we need to put 1 here. So the load gonna have register write 1, ILU source 1, ILU op, add memory write 0, memory read 1, and memory to register multiplexer mem to reg 1. 1 1 add 0 1 1 is for load. For other instructions, the same too. Like for or probably for actually store is kind of similar. Some of them, of course, changing. Like for example, subtract. This is going to change. Or probably if you have add immediate, we're going to have some of these controllers change. Instead of reading one of the registers, the second register from ILU, from register file, we read that from immediate. And what is this part? As you can see, immediate generator, 32 going in, 64 coming out, is extending the value. So 32 bits, we extend that to 64, and we do sign extension. If this is negative, we keep the sign negative. And it's positive, we keep it positive. Okay, that's R type and load and store control signals. We still didn't design controller. We just consider which signals we need. Any question? Okay. Let's go for branch instruction. In your project, you need to design branch as well. branch is kind of tricky because it has some extra parts that you need to consider. And that's coming from here. Branch sometimes, if branch is actually change of program counter means branch. Changing of program counter. Instead of going to next instruction, going to somewhere else. Somewhere else specify with the address that you consider in a code, immediate value. So instead of going to program counter +4, you go to another address that we specify in a immediate value. Like, for example, branch equal is like that. If x1 is equal to x2, go to offset. Okay, so let's complete this circuit here for branch. Imagine I gave this to you for one of your assignment, and I tell you which extra part, or maybe I just ask you complete this data path for branch equal instruction. We have branch equal instruction, and you need to complete the data path. So the data path means which components your data gonna go from program counter to result, whatever is the result. Okay, so for sure start from program counter. Actually, program counter here is important part. After program counter, data going to instruction memory. Instruction memory going to instruction register. It's just one register for instruction. And then the instruction register is get decode, and some part of that, like register source 1, register source 2, and we have also opcode going to the controller, but we are not designing that part. This is register file, and register file going to ILU. Do you remember we had one multiplexer here to tell the output of, this is multiplexer, that specified the output coming from immediate value or from register. What we call that? Yeah, we call that memory to register. Yeah, memory to register. Yeah. Oh, not that. Sorry. ILU source. ILU source. ILU source. ILU source is a control name of the control signal. I didn't put here, but you need that as well, because you need to tell you for branch what is the input of this ILU. Is it coming from register file or is it coming from immediate value? That's coming from immediate value, because in branch equal, you have an offset. Offset is an immediate value. Okay, so, and this ILU doing some calculation. What calculation this ILU doing? Can you guess? Is it doing add? Is it doing subtract? Is it doing OR, XOR, whatever? How we can check these two are equal? We can do subtract, because we have 0 bit as output. So when we do subtract, if they are equal, the 0 bit gonna be 1. So it means they are equal. So this gonna do subtract. We have output that going to memory. We don't care about that part. So, okay, let's go to the rest. This program counter we need another multiplexer, that output of that going to the program counter. This is the design of branch. This multiplexer specify, are we going to program counter +1, +4, or are we going from program counter plus this offset, this immediate value? Okay, so this has two parts. One is program counter +4, and one is program counter plus immediate value that we need to shift that 1 bit. If you remember, when I talked about branch, because instructions are even addresses, always bit 0, least significant bit is 0. So we don't need to save it. But here we need it. That's why we shift it. We don't waste time. We don't waste a space for that. But when we want to access that, we need to shift. When we shift it, we return that 0 back. Okay? And we also need one control, that this control called actually jump or branch signal. Okay, let's go to this area to see how what else. So as you can see, the immediate value coming here and get shift to left as we want, and add that with program counter as we want. So the output is here. So we have this done. And we also have this one as well. That's also done. But how we make this branch? How we make this? Oh, not how we make this signal? It's not branch. It's called another thing. I don't remember it. But don't worry about that. Let us just how we make this select. So we have 0. This 0 need to get AND with branch opcode. Branch is not the opcode, it's a signal that coming from controller for branch instruction. When computer decode branch, when controller decode branch, it's gonna active this one. But we still cannot do it. We need to see if the condition is okay. How the condition is okay when this equality exists, when this 0 is 1. So we AND them together, and then the output gonna go to multiplexer. I made that a little mess here, but we have a clean picture. We're gonna see that soon. Just gonna change the color here to don't. I just wanted to show you how we can actually make the data paths connected. So this is those extra parts that we need to add to data paths. That's why we have another step for design after making data path. That's called refined data path. Refined data path means adding extra multiplexers, adding some extra gates. That AND gate is something extra. These multiplexers also extra. This shifter is extra. They are in that step. Okay, so that's a branch. So for branch, the control signal is going to be like that. ILU source, 0. ILU source need to be 0. And 0 is for a register, because we need to get these two registers. This immediate going to go just for computing the next address. So this is 0, means it's coming from register file. Register write is 0 because we are not doing anything here. We are not resulting result. We are not actually storing result in register file. Where we store result then? Program counter, exactly, as you can see here. We're writing that in program counter. Great. So we don't write it back here. That's why this is 0. Memory read, we don't work with memory, both 0. Branch is 1 because instruction is branch, and ILU operation is subtract. Again, why is subtract? Because we want to check equality. We subtract them, the output of the ILU. ILU always has one extra output called 0 output. This 0 is help us for these cases. Okay, now that we learn branch, let's do it all together in one full data path and control the, make the controller. That's a full data path, but not controller. We have one controller that makes these blue signals. We have one controller, is a combinational logic, even it doesn't need clock. I'm going to make those. As you can see, all of those parts here connected nicely. This program counter get result from program counter plus 4 or program counter plus shifted version of immediate value. That is a place that we want to jump. Anyway, if we draw this table, this is truth table, like a normal truth table. For all of instructions, for this computer, we have this type of instructions. R type, load, store, and branch. Imagine in this simple computer, we just need these instructions. But these instructions coming from opcode. Like, for example, opcode for R type is something 0, 1, 1, 0, 0, 1, 1. It's 7 bits. But to make it simple, we just consider that I1, I2, instruction 2, instruction 3, and instruction 4. So let design register write. If we draw the truth table, as you see, this is the truth table. Register write is equal to I1 plus I2, because we have 2, 1 here. So this plus this. We call that I1 and I2. Why we didn't write that? Because I1 corresponding to this and I2 corresponding to another opcode, like for example for load, we consider 0, 0, 0, 0, 0, 1, 1. Okay, so I1 is what? Opcode 6 bar and opcode 5, opcode 4, opcode 3 bar, opcode 2 bar, opcode 1, opcode 0. So we add these bits together to make this I1 to I4. We just order them together to make our register, to just make it simpler. So for all of these input controllers, we can make this. This is for Carnot, even doesn't need Carnot map because it's so simple. But simpler than that is just write the Verilog code. As you can see, for Verilog code, you can just have a case. Opcode is that for R type, for the word, for load, for a store, for branch. The initial value is all 0. That's why we didn't fill the sum of them. Okay, there's no time, but next class we're going to talk more about. I'm just going to show you. We have 2 controllers. one for main controller, one for ILU, and that's the controller. The controller is going to create or make all of these signals getting just from opcode. And we have two controllers because this ILU output is just 2 bits, but we need to check those fields, 7 bits fields and 3 bits fields, to consider other instructions for R-type. R-type has more instructions. Okay, guys, have a good weekend and see you next class. Please start your project as soon as possible. If you have any questions, you can send me email.